All right, now let's attempt a more difficult second order differential equation using Laplace transforms. So we're going to have this equation, d squared y over dt squared plus 2 dy over dt plus 5y is equal to a function driving, which we'll call h of t, which I'll explain what that function is at a moment. But let's start from rest in the 0 position. And let me write down what h of t is going to be. It's going to be what happens if we apply a force of, say, 5 for the first 7 seconds, and then we let go. And this corresponds to the way we can write this in a way that we can actually compute. This is 5 times 1 minus the Heaviside function. So recall the Heaviside function u7 of t is something that is 0 until time 7 and then becomes 1 for all time. So it's like turning from off to on. We need something now that turns from on to off, so that's why it's 1 minus u7t. All right, so there's what we need, and let's start computing here. We want to take the Laplace transform first of the second derivative of y, which we have computed. It's s squared times the Laplace transform of y minus s times y at 0 minus y prime at 0. Those are going to zero out in a moment. Now we have 2 times the Laplace transform of y, which we know is s times, or Laplace transform of dy over dt, which is s times the Laplace transform of y, minus y times 0, which is also going to disappear. And this is all plus now 5 Laplace transform of y. And this is all equal to 5 times the Laplace transform of 1 minus u7t. Okay, now we got to clean some stuff up. Okay, on the left-hand side, we have s squared Laplace transform of y, 2s Laplace transforms of y, it's over here, and 5 Laplace transforms of y. And all the other terms are 0 because we are assuming that we're starting from rest at position 0. And on the right-hand side, we have 5 times the Laplace transform of 1. The Laplace transform of 1 is 1 over s, which we can find on any chart of Laplace transforms. And then if we recall, the Laplace transform of the Heaviside function is e to the minus 7s for the 7-second delay, and then divided by s. And there's a 5 here as well. All right, so there is our situation here. Now we need to isolate the Laplace transform of y. So let's do that in the next screen. We're dividing both sides by s squared plus 2s plus 5. We get 5 over s squared plus 2s plus 5. And then we get minus 5 times e to the minus 7t, sorry, 7s, divided by s times s squared plus 2s plus 5. Okay. Now it gets a little bit difficult. What we need to do is do a partial fraction decomposition. Now, one thing to note before we start here, it looks like we've got 2 to do, but really we only have 1 to do because this e to the minus 7s we can just pull out after we figure out what this one is. So it's only 1 to do. So we have to look at 5 over s squared, or sorry, s times s squared plus 2s plus 5. Now we have to figure out what are the factors of s squared plus 2s plus 5. But you will note here that this does not have real solutions, right? B squared minus 4ac is a negative number. So this only has complex solutions, so this cannot factor any further. So we're going to have a term which is like something over s, and we're going to have a term which is like something over s squared plus 2s plus 5. Let's say this is a, and this, we go down in degree 1, bs plus c. Okay, now let's figure out what these terms are going to be here. So 5 is going to be equal to a times s squared plus 2s plus 5. And then bs plus c is going to be multiplied by s. So this is bs squared plus cs. Let's gather like terms here. We have an a plus b s squared. We have a total of 2a plus c s's, and we have 5a. Okay, so now we kind of work backwards. We only have 5 on the left-hand side, so that must mean that a is 1. A being 1 immediately implies, because there's no s squared on the left-hand side, that b is negative 1. And there's no s on this side, so that must mean that c is equal to minus 1/2. Oh, it's not 1/2, 2. Excuse me. Right, because 2a plus c must be 0. Great, so now we can decompose this. 5 over s times s squared plus 2s plus 5 is equal to 1 over s plus s plus 2 over s squared plus 2s plus 5. All right, so what we have to do now is we have to figure out how to complete the square in the denominator. So let's start on another screen. This is the most difficult part here. Right, we are dealing with the fact that 5 over s squared plus 2s plus 5 is equal to 1 over s minus s plus 2 over s squared plus 2s plus 5. Now, recall, in order to do, we're looking for a reverse transform that's going to have sine or cosine type properties. And to do that, we need to have something squared in the denominator plus something else squared. We don't want this s in the denominator at all. And so to deal with that, what we have to do is we have to complete the square. So this is s plus 2. Now to complete the square with 2s, the only way to get 2s with the square is to have s plus 1 squared. Okay? So s squared plus 2s will be part of s plus 1 squared. But there's another part, there's a 1 squared. So I can take that away from 5, and now I have the exact same thing as I had before. So now I can write this as follows. 1 over s minus s plus 1 over s plus 1 squared plus 4. Because I need to write it in a way where I could recognize a sine or a cosine. And then here, minus s squared, or sorry, s plus 1 squared plus 4. Now there should be a 1 here, but if there's a 1 there, we can't do anything with it. It doesn't look like a sine or a cosine. We need this thing up here to be a 2, right? So we have something squared here and the original thing here. So I'm just going to put a 1/2 out in front. Okay, this is equal to the same thing, but it's going to allow us to actually do the transformation. Okay, so 1 over s is the transform of 1. Now this one, this looks like a cosine, right? Cosine is s over s squared plus omega squared. So this is like cosine of 2t. However, we have this s plus 1, but recall that's just a time shift. That was that second principle we used. So this is going to be, and the time shift we get by doing an exponential. So now this is y of t. And then we have another point here. This is a sine, and it also has this exponential time shift thing going on. So it's e to the minus t sine 2t. Okay, so that took care of the first of two terms we had. We had this 5 over s times s squared plus 2s plus 5. And then we also had minus the same thing, but multiplied e to the minus 7t. Or, e to the minus 7s. And that is just going to involve an actual time shift. So this is what we get for the inverse Laplace transform of this part. And now we're going to have this second part, and I need to deal with that in a moment here. So I'm going to clear the screen and address that part. There we have, we're looking for the inverse Laplace transform of e to the minus 7t times 5 over s times s squared plus 2s minus 5. So if we multiply by an exponential, oh, this isn't a 7, this isn't a t, this is an s. If we multiply by an exponential in Laplace transform world, that corresponds to a time shift. Recall, the Laplace transform of a time shift is just a multiplication by an exponential. And we know, okay, this f of s, this is the Laplace transform of the original function f. So we know this. We know this function. We already did this one. Okay? So the full answer now is as follows. We have what we had before. That's the 1 minus e to the minus t cosine 2t minus 1/2 e to the minus t sine 2t plus a time shift of this function. So 1 minus e to the negative t minus 7 cosine 2t minus 7 minus 1/2 e to the minus t minus 7 sine 2t minus 7. And this should be in parentheses here. We're time shifting by 7 seconds. And final bracket there. Barely fit that in there. So we've got two terms here. This term does not come in until 7 seconds later. All right, so there is our solution to a more complicated second-order differential equation using Laplace transforms.